All right. So let's get back to our exercises last time. To go to my lecture, we're going to do some extra exercise. So everybody, I hope, has gotten BoneJ as a plugin. And we did this basic exercise of reading in a sphere. And we can redo that right now. But basically, you read in one object. And here, one important thing, especially in the literature, to think about or to follow is that object of interest is typically called foreground. An object that is not of interest or everything else in the image is background. Now, you always have a liberty in what are you calling, what is black or white in the image. That's really a matter of choice, and there is no right and wrong, but you do need to understand what is the algorithm you're working with, calling foreground and background. So that's, with that understanding, our sphere, our object of interest, our foreground is here white, so that's 255 for image J anyway, and black is 0, that is everything else. So when
Excuse
we analyze that, yes?
I can't see your screen.
Thank you for that. I keep doing that. So I start talking and I don't share the screen. All right. So now, okay. See it now?
Yes.
Thank you. So make sure to remind me when I'm not doing that. So essentially, I'm just reviewing what we did for the exercise last time. So it was a sphere. So let's actually get it again. So whenever validating algorithms, I guess that's really going across anything, but especially in these algorithms that are working with images, try to find the simplest example that you need to show something where you understand something, but not simpler, if you will. So in that sense, one object, one sphere, is sort of topologically equivalent to one blob of anything that we can possibly look at. And that's a good thing to start from. Now, basically this sphere, so we're going to actually make it a little more complicated today. So let me read it in. So import raw. And there was, apparently I have done a whole lot of things since I need to figure out where my open raw, I need my teaching. So I need a topology exercise and my sphere. Okay. So it is 100 by 100 by 92. Okay, so here it is. I'm going to blow it up a little. So this is my digitized sphere. And it was really saved from one of those image look at the, I think it's in this file. There's a part where we can look at the what is the type of a neighborhood that the morphological algorithms are considering. So it's really saved as an object from there. So did everybody open it up? So let's just redo quickly what we did. So your BoneJ should be sitting, you can search for it, but it should be sitting as a plugin that was separately added. So any kind of plugin that you externally add to image J or Fiji is going to sit in plugins. So we're going to do particle analyzer. And I'm going to avoid graphical results right now. That's the part. Who had trouble with it? Have you figured it out? Javier, did you have trouble? with graphical results? Have you figured it out at least on one machine?
Yes, I already fixed that.
Okay, so if anything is going to go wrong, it's the 3D visualization that is going to go wrong on a computer. There's, for one, it's intense. And then there's a lot of machines, like especially if they're simple, if they're your phone or their tablet or a simpler laptop, they're not necessarily, they're often sharing memory with the main computer. So the video card memory is basically sharing the computer with the regular sharing with the regular working memory of a computer. And if there's anything intense coming along in terms of visualization, that's going to slow down the computer or not work and so forth. So the better the video card and the more, so if you have a separate video card, that's the best. And the more memory that video card has, that's better. If you're looking for scientific visualization, it's going to work the best on gaming laptops or gaming computers, because gaming is very intense. So basically look for reviews of computers that are best for gaming. They're actually going to have visualization down and worked out well. So that's just a general idea. So if you're, next time you're buying a machine and you want to actually have something that works well in visualization, those are typically gaming laptops. So what we're going to quickly here is calculate, we're going to calculate Euler characteristic on something that we understand. And if you remember Euler characteristic, there was, the main thing was the number of connected components, which in this case we should get one. It's this one sphere, right? And then we should get zeros for everything else, handles and cavities within this object. Okay? So in that sense, we feel we understand this object, so we should see what we get. And there's a results table that should show up when it's done, but it's working on it. So you also see, so there is a number of pixels that this is analyzing particle, and it's throwing into the analysis anything that you have selected to analyze. So you can see X, Y, Z. There's surface area. We're going to get to that later. Enclosed volume. There is inertial, moments of inertia. And there's basically Euler characteristic is 1. Number of holes is 0, and number of cavities is 0. And we don't need beta 0 because we can get it, we can basically calculate it from Euler number. And then something that is also useful in general is sort of looking at this major, minor, and intermediate radii of a particle or any object. And specifically if you have a sphere or ellipsoid or a simple object, this makes a lot of sense in characterization to look at. The more complex the object, the less it makes sense, or it's kind of integrated in a way that is hard to analyze. But this can tell me that this is a spherical object because major, intermediate, and minor axes are all very similar. If I have something elongated, so for instance this, right? This is a cylinder, so it's going to have one major axis that is much longer than the other two, and the other two are here, right? So I will have two that are very similar but smaller than the major one, and that gives me an idea that the object is cylindrical. If I had a plate, which is like my hand, I'm going to have two major ones that are, or my major and intermediate will be large and similar in value, but this minor one will be way thinner than the major. So that gives me a plate-like object. So in that sense, analysis of these individual objects or looking at their radii can be a useful characterization exercise. So back to our Euler characteristic again. So we are given a number that we understand how it works. So this is a good thing to verify. Now, what happens if I kind of mess up this image, or if it's noisy for some reason? So we can add Speckle Noise, and I think it's in image. No, noise. Let's do salt and pepper noise. So in process noise, salt and pepper. add salt and pepper noise to all of these 92 images. So we're going to do yes. So this is literally, it's a randomized process in which you just add the opposite phase to the one that is here. Okay. Let's now do this analysis again. So this is extreme case, of course, but this is basically what the result of a poor segmentation could look like. And let's say that the only thing I want to do, so analyze particle analyzer. And I'm going to really just calculate enclosed volumes, surface area, and Euler characteristics. I'm going to turn off everything else just to simplify things. So these three things. And I'm going to turn off all of the visual. Well, this would kill the visualization, I can tell you right now. And your laptop might not perform well. Okay. Let's go for it. For one, my number of connected components has changed a big time, right? Okay, where are my results? Apparently, I have more than 10,000 particles now. So it went particle by particle. So now every little speckle here has been interpreted as a separate particle. And you can see what noise does to that. And it's nearly impossible to basically get to the large one. Where's my largest one in volume? It's going to take some search. This is where it would be better to export this to an Excel and search, or sort. Here we go. Here it is. This is probably the one that our original sphere, the one that we are interested in. And you can see what happened to the, I now have about over 5,000 small cavities. Those are all of these speckles. Each one has been interpreted as a cavity. And that has influenced my Euler number in a major way. So that's not something we want in a robust analysis, especially if this is not a true feature, but it's really just noise. So the surface area and enclosed volume are not necessarily all that different, because volumetrically these cavities are very small. So this is going to have a huge impact on volume. However, it can throw off these morphological operations big time. Okay, any questions? Okay.
Well, just one question, maybe it's not that important. So we said, like, to calculate the Betti numbers, this formula corresponds to the Euler's formula, right? Which is like vertices minus edges plus faces.
Right, correct.
So if we do that for the sphere, beta 0 turns out to be 1. So like a sphere has one vertex? Or like, is there
Yes.
something wrong?
But it's now the number of cavities. So you have beta 0, right? That sphere, even though it has speckles within, it's still one object. But now suddenly, because of noise, that object has a whole lot of cavities. Each speckle is one voxel cavity.
Yeah, I'm talking about the without the noise when we did the
Oh,
first
without
one.
the noise, yes.
Yeah.
So it's
Okay,
1
so-
minus 0 plus 0 for one non-noisy sphere.
Okay, so we consider a sphere has one vertex?
Yeah, because it's a solid sphere. It's this case.
Okay, cool.
Okay. So if the sphere is hollow, so it has a hole inside,
Mhm.
then the number of cavities is 1.
Okay.
So what that noise did is that every little speckle is one little cavity.
Mhm.
Right? Now, if those things are real, sometimes that's real. Right? But if it's not real, then it's a problem. Like if it's just noise, these what I'm showing is this: the algorithms are very sensitive to the noise because they actually go pixel by pixel and assemble. They assemble these numbers iteratively over every pixel and just look at the differences. Does this pose a difference to the larger object? And then it moves on. So it processes everything.
Cool.
Okay. Any other questions? Okay, cool. So now we're going to actually look at the very small equivalent of these trapped non-emitting phases. So there was a paper that basically analyzed the topology of the trapped phase, and that can be useful characterization, especially in three-dimensional cases. So we're going to do a very small version of it. And I have shared it in this prepared digitized subdirectory. There is 2 files. So I'd like you to open them up. So first one is what's called mask segmented, and it's 112 by 112 by 112. Unsigned binary character so basically it's an 8-bit image. And I would like you to quantify Euler characteristic of the pore space. So we'll look it up. And these are 0-1 images. So this is how often segmented images are interpreted in other software, non-ImageJ. And I want that to be part of this exercise. For instance, a lot of DigitalRocks portal images have their phases that are segmented as 0, 1, 2, if they have, for instance, 3 of them. So something like that is pretty common. Again, it's a matter of choice. There's no way to pre-design something that works the same way for everyone. So I want you also to make ImageJ version of segmented images from them by essentially multiplying them with 255 and inverting as necessary depending on which phase you want to analyze. And then the second image, trapped oil, has basically identified trapped phases, a trapped oil phase, and that's literally this. So basically, this is a sphere pack. You don't see my spheres. You remember, this is my favorite little show. So basically, you will have an image of these trapped oil phases within. And you know that in my, let's see if I can trap a complex one. You know that this kind of, so some of these trapped oil phases, let's see if that happens right now. A lot of them are simple and topologically equivalent to a sphere. But sometimes, depending on how this process works, I can get sort of like a ring. There we go. Sort of a ring. It's still moving. And that ring, so definitely the top phase here, let's see if I can see. So some of them actually are kind of ring-like and actually have handles, these trapped phase. So one can presumably see that by analyzing Euler numbers. There is actually one, it's gonna be hard for you to see, but some of these on the bottom actually have kind of a ring in them around sphere contacts. So basically some of these trapped blobs are not topologically a sphere, they're topologically a donut or coffee mug or however you want to call that. topology. Anyway, I don't know what's now in this small one, whether we have any of those in there. Yes, probably one. So this is how it looks like in visualization, but let's open them up and work with them. And let me know if you have any issues. And we're gonna take the sphere. Actually, let me take, okay. Doesn't matter. Okay. I'm gonna load import. So why is this image pitch black?
Because it's only zeros and ones.
Right. So the scale by default for 8-bit images goes to 255. So white is considered 255. 0 and 1 compared to 255 is pretty much 0, and that's black. But as you walk around in the middle of the image, you will see zeros and ones show up as values. So everything is fine. You can do math, image, or rather process math, and we can multiply this by 255. There we go. And now they show up. So these spheres are obviously not very, there's not a lot of resolution to all of them, but they are actually all equal spheres. This is a subset of the Fini packing, whose information actually sits on the DigitalRocks portal if you needed a larger example. So that is my pore space. Now, pore space right now shows up as 0, and the grain space is 255. So if I were to analyze this, my foreground or object of interest for a lot of these algorithms would be 255. So we'll invert that. So we can invert. And one of these days I will know shortcut for invert, but not today. All right, so now my object of interest is 0, and that's my pore space. So let's look at the I'm gonna go with everything to see whether visualization will pop up. So let's actually see the three-dimensional visualization of this packing. And there's apparently 4 disconnected little voxels that are all on this list. Did everybody get this?
Yes.
What is my number of connected components for the largest? Beta 0.
451 minus 450.
So I have number of holes is 452. Euler characteristic is the number beta 0 minus beta 1 minus plus beta 2. This is 0. So it's 1. 1 minus 452 is minus 451. What are these holes about? Where are the holes? What is a hole? These spheres within are all interpreted as holes or handles. These objects. They're connected to the outside, technically. They are interconnected in 3D. That's something to check with the large phase, but because I have sort of a ceiling on top and sides that connects them all essentially together into one object. So this is basically the influence of all of the spheres that are within, that this pore space is wrapping around. Is everybody visualizing that from this? And that's why I'm getting this count of holes as 452. But there is one connected component, and you don't get beta 0 here because you can compute it from Euler characteristic beta 1 and beta 2. Yes? If we did a connected component analysis that find connected regions on this image on the pore space, I would get one connected region. Okay? Excellent. Now let's actually look at the other image. I'm gonna put this one, I'm gonna turn off this. Oops. So we'll import the other one. And that's my trapped oil. And again, it shows up as 0 and 1. I'm going to multiply it by 252, 255. And you can see my blobs of interest show up as 0. So I'm going to again invert the image to get my objects of interest, which are these trapped blobs, to be 255, or that's my foreground, that's my object, or multiple objects. See the blobs? Let's now analyze this one. No. Click on the image before you do it. Or else it's going to claim there are no images open. What? Okay. It is 8-bit. Is anybody else getting this? Oh, I opened another Fiji. Don't open two. Okay, so this one I can close. All right. I'm not interested in moments of inertia for now. Well, yeah, let's actually leave them. No, I'm gonna just show surfaces. There we go. Woohoo. Oh, that's pretty. Sorry. Did everybody get here?
Yes.
Yeah.
Is everybody else excited about these little blobs?
How
Or
does
is
it
it just-
assign like different colors for different blobs?
It just knows individual objects. So I think it said something like gradient, so it just actually has some default values. Similarly,
Mhm.
like that find connected regions, it just has a default built in to go over certain colors. And here it seems that the gradient is sort of between greenish and reddish colors.
Mhm.
But can we assume that each element has a different color?
Yes. And it probably does. Question is, can you see it? Frankly, I don't differentiate this and this as different, but they're probably different as numbers. Right?
Okay.
So it's better to go with the rainbow coloring. But again, the coloring is just a matter of choice and preference. These look pretty, but it's I actually like this gradient between red and green, but it's hard to differentiate. At some point, no matter what, if you have a person looking at it, we can't differentiate well more than 20 colors or so. I mean, we can if we really look, but not quickly. So that's a matter of, it's a very good question where you can change this, change color. Here we go. I don't know what's this gonna do, but we're gonna find out right now. No, it doesn't do much. I think in this initial,
I think it's before you run it, you see the
before
option
you
of
run
gradient.
it, there's something called like I clicked on it and it said gradient, so it probably can do something else. But again, color is relatively easy, so just understand that it's fairly easy thing to change. It has a default mapping between object and the color, and how you scale that and how you interpret that color is really up to you, and what kind of color scheme you choose. It's really just dressing things up.
Because technically these are like the same phase, even though they're different objects.
Yes,
So
but
ideally you would
in
want them
this
the same.
process, it found individual objects. So it has counted them in the process, so it does know individual objects, right? And because of that, it's able to differentiate them in the picture. Like this whole particle analyzer is about analyzing individual particles. And in this case, they're actually sort of topologically spherical, right? So they're actually individual particles. They're not always individual particles, or sometimes they're merged or fused together. So that's, again, and it seems that there we can adjust some sort of I didn't play with this particular selection of image 3D viewer, but you can change the selection at the beginning. It looks like you can do it at the end. But again, that's dressing up your results. It's important for distinguishing things. If you remember, there was in the main Fiji, I don't know that these, well, let's test. I don't know that these lookup tables, they're called lookup tables. How do you assign color, because it's an artificial assignment to whatever it is that you're seeing in the image, the actual values. So I don't know that these lookup tables will translate to image 3D viewer, but let's actually see. So let's change to something, anything. I don't know that it's doing anything effectively, but it's working on something.
I think it's working on the original image before we
I would
run
think
the...
so too, because I don't think this 3D viewer is a plugin, so it doesn't necessarily respond to the choices made in the original Fiji. That's also important to understand. Somebody plugged things in, that doesn't mean that they integrated with the rest of the Fiji software so that all of the functions can work on whatever plugins. Yes, I think it's whatever it is, it's working on it real hard here in the background. But I don't think you need to do this in 3D viewer, just by the logic of it. Okay. Back to our trapped oil blobs. Well, here they are. This is their volume. I might be interested in how large they are, how many I have. This is obviously a little noise one. This one I could remove from the analysis if I wanted to. But let's look at their Euler characteristics. So all of them, without looking at the results, all of them, they appear topologically to be a sphere. Does everybody agree with me? I have single for each and every one of them, separate one. I have a single object. I don't seem to have, well, from the surface, I don't see visible cavities or I don't see handles, and cavities, well, if they exist, they're inside, so they would be hard to see. So let's now actually investigate that that's the case here. I can indeed see, as I scale this, okay, that most of them indeed have number of holes and cavities is 0, all of them actually. Okay. And the Euler characteristic is 1, which makes each of them have, so these are, again, they're analyzed separately as each separate connected component. So they're one. If I analyze this as entire phase and find connected regions, I would basically, the number of them would be the number of them would be how many? 1, 2. Has anybody counted how many? There we go. So just to, and I think Faizan pointed it out at the beginning, essentially the way this algorithm does, it's a particle analyzer. So even though initially we started with the phase, it looks at each connected component of that phase and sort of analyzes it separately. Okay. So technically each line here has a connected number of connected components is 1 because it's analyzing each particle separately. This is a particle analyzer. And then for that particle, I'm looking whether I have any holes and cavities within. What we started with was that pore space, which was a, so basically to sum up this entire phase, I would just actually sum over all of these contributions up. So my Euler number would be positive and around, what is it, 20-ish of them, right? So my Euler number went from something very negative, minus 451, which was there because of the number of holes that I was wrapping around spheres, and those were counted as holes in my pore space. So I went from minus 451 to positive 20 or so, because now my oil that used to be around everywhere, after imbibition process, the water went around it, snapped these individual blobs, and those blobs are now individual components. So basically, if I look at all of them together, it would be sum up of all of these numbers. So I have no holes anymore, and I have these individual numbers. So I went from minus 450, let's say, to 20. Does that, and this is a smaller subset, does that actually agree with the finding of the paper that I talked about to begin with here? Here we go. Are we in agreement with this finding? With the understanding that we looked at much smaller image. So again, it says that positive Euler values indicate that object exists as disconnected isolated blobs. And we did, if we sum up all of the components for our trapped blobs, we got about 20, right? So we were around here. And negative values indicate more connected and complex fluid blob structure. And when our entire force space was this more connected fluid structure, that was our minus 450. So we were somewhere here, right? So we technically agree with this finding. I think this is flipped. So these were, no, these were initial values and these are final values. I'm not sure what is original versus an initial here, but it's taken from the paper. Okay. But this finding we definitely agree with. Yes? We confirmed a finding in a paper. Technically, there's actually a number of images. This is coming as your homework. So I initially planned to have a separate additional segmentation homework and then this analysis of blobs. I'm going to actually put it together into homework that is going to be assigned today, since I figured that you're working on your write-up anyway. So that's going to be assigned today, and you're going to do a segmentation on an image, and then you're going to do the Euler characteristic analysis on one of the images on the DigitalRocks portal. In 3D, it's going to be 3D image. All right. Okay. I will not go into the details of the algorithm that is used for this calculation, but basically it's moving through, it's looking at local neighborhoods and summing up all of the details. And that's one way to actually tackle finding Euler characteristic of complicated objects, because they're actually a sum of all of the contributions in individual neighborhoods. So you can, if you're interested in such things, there is basically both BoneJ, paper on BoneJ, and the quantification of connectivity in bones, which is essentially 3D connectivity analysis similar to our interest is oil blobs. For bones, it's a different application, but it's a very similar pore structure. Yeah. I'm just going to point out a number of things that we're not going to have time for, but it's something that is possibly of interest to you. One thing that is done a lot is two-point statistics and analysis of two-point correlation functions. It really literally gives a probability ultimately of two objects at lag. So let's say 2 pixels at 50. So here, if I take 50 microns separation in my image, so this is obviously converted, these microns means that I'm converted to physical values. What is the probability of being in the same phase or in the same object? And there's it's a statistical measure that is straightforward to compute, but it can take quite a bit of computational time in complex images, and is often used in both for characterization and for reconstruction of three-dimensional structures. And I'm just going to leave it at that. It's been traditionally used a lot to analyze images, but it's not always easy to interpret. So I tend not to rely on two-point statistics. I would use it only if it's needed for three-dimensional reconstruction, which is a topic that is too advanced for our purposes in this course. One thing that we are going to spend a little more time on is Euclidean distance and Watershed, because those are very useful morphological operations. They're essentially morphological operations. Minkowski functionals are becoming ever increasingly popular to analyze pore structures and characterize pore structures in general. Different types of percolation analysis, fractal dimension, those all technically exist in image J and you can play with them, but there's just so many things that we can actually fit into one course. So I think Euler characteristic is one good starting point, but other than that, we're not gonna focus on Minkowski functional percolation or two-point characteristic, two-point correlation function. Okay, this is our intro morphology lecture, and now I'm going to go into the next topic. But before I do, any questions about this? Before I close it all off, gonna interpret silence. Yes, questions.
Could you please show me back where you were seeing the positive and negative values for the Euler function?
Yes. So positive values here for my trapped oil. This result basically worked on every individual blob. So to get actually for all or entire oil phase, I would just sum all of these up. So for the entire oil phase, my Euler characteristic is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yes?
Okay.
So 17 number of holes and number of cavities still stay the same. What's good about these things is that they're additive. And that's actually how algorithms work. They just pile through all of them. Yes? So 17, so Euler characteristic for entire oil phase that is in this trapped blobs is 17, and I have no holes and cavities. So really what I have is 17 little spheres, or they're topologically spheres. Yes?
Okay.
And that's important to know because my trapped phase could be actually complicated. Let's say that my trapped phase partially wraps around one of the spheres, which it could. That sphere is now actually a hole or a handle in that object, depending on how is the, if that sphere is somehow connected to the outside, it's going to be interpreted as a handle. But that really depends on how I basically, in that image, I had those planes on top and sides, which essentially connect all of the spheres to the outside. And that makes them a handle rather than cavity. Cavity is completely enclosed, completely disconnected from the outside. You see that?
Okay.
Yeah. So, and that's important. That's why it's important to start with something relatively simple, just to see how these abstractions, they're abstractions, how do they relate to the actual object you're seeing? So that you can interpret. So start from something you know. And then in that pore space, when we looked at just pore space, we got that Euler characteristic. I don't know that I have that as a printout. No, so those results got overwritten by these, but the Euler characteristic was minus 451. And that was his holes or handles were 452, right? And then some, yes, and cavity 0. Those were our three numbers. And again, that's why all of the spheres that my fluid phase was enclosing, they weren't characterized as individual object, individual cavities, because for one, they weren't properly disconnected from each other because they're digitally actually connected. And they were digitally connected to the outside because of the sealing planes on top and bottom. And that's why they were actually interpreted as holes, or sort of like just like a handle on your cup.
Okay.
And so this thing here is not enclosed, it's actually connected to the outside. That's what happened to those spheres. Actually, here it's a great example. It's repacking. So if I basically, okay, if I put a sealing plane here that is also this purple color, suddenly all of these objects are connected together into the other phase, and that makes them a whole. They're not completely enclosed by air phase. Yes, sort of, a little bit, yeah. Okay, so that's why my pore space, it had one connected component, these 400 and something holes 452. So my Euler characteristic was 1 minus 452. It was minus 451. So it's one object, but it's a pretty complex object. It has these handles and cavities within. This one didn't have cavities. But basically this negative number, if you get that like connected component is 1, but otherwise Euler number is negative, Euler characteristic is negative, that identifies this object that is kind of wrapping around things and is convoluted, even though it's connected. And that's porous media, pore space. Almost every porous medium, pore space. Right? Essentially both solid phase and pore space are these complex objects that kind of wrap around each other. They're bicontinuous, they both connect across, and kind of wraps it around in three-dimensional space in a complex way. And a negative Euler characteristic for a connected object tells you that. Now, in absolute sense, that number is, of course, larger the volume you look at. So our number did not get to, in number of connected components, did not get above 17. If I looked at 8 times larger pore space, I would have 8 times more connected components, right? So this is where you would need to start quantifying things, actually relate them to physical volumes and look at number per volume to compare different things. Yes?
Okay, thank you.
Did I just make it more complicated or? But essentially, like again, if you have one connected component, but your Euler characteristic is this highly negative number or something that is like off from that one, that indicates this complexity of things wrapping around each other and having things like handles, right? Or even completely enclosed objects. So if I had a cavity within that I don't even see, right? That also adds to the complexity of the Euler characteristic. And you can monitor changes. So a lot of times it's like you look at your, whatever it is that you're quantifying, and you start from a number and you see how it changes in the process, and that can possibly tell you something about the physical process that is happening. So here I'm trying to connect this to the physical process of trapping or non-wetting phase. Happens to be something that I'm always excited about, right? So if I could basically also look at this dynamically, if I had images for all of these intermediate stops in the process that you're looking at right now, I could see what is the path in that Euler characteristic space. And that would be, if I'm analyzing multiple experiments, that could be something to simply look at. How does it happen, and relate possibly to the viscosity of these fluids and number of other. So it's a way to characterize. Yes?
Yes.
Gives you a number you can compare. It's actually, so this is a totally aside. My color picker is still working here. I don't know if you something is still being processed in the background. I might need to turn that off. Okay. All right. Now let's go to a related but new concept. And unrelated point number 2, as you know how they say that you shouldn't be touching your face these days. I didn't count, but I must have touched my face in this video. Like now that I'm looking at myself, I'm becoming aware how many times I actually touch my face. I did wash my hands before teaching, but I'm constantly into my face. So I hope you're a little better at not touching your face, and because that can be related to your health these days. All right. All right. So don't be like me. Don't touch your face too much. Okay. We're going to go to an advanced topic called skeletonization and medial axis. My neighbor decided to cut his grass. I apologize if that influences the quality of the sound in this video. Alrighty, so what is medial axis? It is essentially a thin representation. Literally what we are looking for is a skeleton. If you imagine a person, we do actually have a skeleton. It's a physical skeleton. It's not necessarily result of any kind of morphological analysis, but that skeleton is carrying our weight and is mechanically enabling us to actually stand up and walk and so forth. So how our bones are connected to each other is related to our ability to move. So we're looking for getting an image analysis version of that, if you will, from the actual object. So the basic idea is that we would like to reduce a 3D object to a line-like or a thinner version of the object. And the practical applications are many. One would be actually visualizing how things work. Second one would be actually mechanical analysis of the object. But also makes a more compact representation of the object, and therefore it's easier to analyze. But it preserves one key feature that we're looking for is preserving connectivity. Essentially, if I'm looking at this ballerina or dancing lady, basically, if I want to know whether I can get from here to here within the same object, well, technically that's equivalent to finding a path along this red skeleton from here to here, and that path is way easier to find on this, what is a graph of lines, these red lines, than it is in this entire three-dimensional object. So it's a simplified version of this that preserves connectivity. Okay? So some example applications would be some virtual navigation, visualization, registration of different objects to each other, right? As this lady moves, maybe we can actually reconstruct the movement way easier than we would with the full image of the dancer. And also shape recognition, right? And in porous media, the specific application is finding out the pore, what's called pore throat network of the pore space. And that enables a simplified flow stimulation, and we're going to have a separate lecture on how that works. And this is something that you're actually trying to, some of you, there's a group of you trying to extract a fracture network from image. So basically something that would identify individual fractures in this image. So this is a related question. And there's, one can actually analyze it different ways. We're going to first start from 2D. So how do I define where are the candidates for these skeleton objects? One simple, what's also related to the grass fire algorithm that we mentioned, is start a slow burning fire, numerical fire, from the object boundaries. So here is a boundary. Here's a boundary, here's a boundary. If I started fire from here and here, and that fire starts, that fire starts burning at the same rate, I would get something like this, right? So at some point, these fire fronts would merge. And at that point, I stop, okay? So these basically the lines here, the line here, so my object is white and I started from this rectangle boundaries. So basically the lines here show where this fire, two fires met and stopped. And that's what it's called grass fire, because actually two fire fronts could extinguish themselves in reality that way too. So then my medial axis candidates are actually these lines that you see here. Now, why did these two fires extinguish themselves? So if I look at this circle here, at this point here, I can see that it's equidistant from this boundary and from this boundary, which is why this fires merged and stopped right there. So basically I can draw a circle And that circle is in contact with at least two boundary points, this one and that one, of this object. So that mathematically defines where these candidates are. So if I can inscribe a circle and that circle touches at least two boundary points, I have actually found my skeleton, we call that skeleton candidate. Okay. So I could do that in 2D, I could do that in 3D. So this is a three-dimensional version of it. Okay. So if I look at all of these on this plane here inside cuboid, okay, I have an entire plane of voxels where I can draw this inscribed sphere, right? So each of these points is a center of, actually they're continuous, right? But they're center of inscribed spheres that are, and each of those spheres is touching both top and bottom boundaries. And whoops. And then I have also these objects here. So you can actually then see that this is a continuous space definition. And this is what we would like to see. However, in digitized space, we already noticed that our connectivity is not always what we expect it to be. Now, here's some medial axis candidates in 2D. So I actually took some images down and found, we're going to get to calculating these later, but basically, if I have an object like this, this is how my medial axis will look like. I will see that I don't have perfectly straight lines, and in the digital world, those can be a little difficult. If I had an enclosed object, so this is my object with a cavity, if you will, I will have medial axis going around it, like here. Okay, so the white object here is a medial axis going around this. And then if I have any kind of like a little surface crevice, my initial medial axis, which was supposed to just go through the middle of it, will try to reach that crevice. And if you see this structure will replicate itself in this small little rectangular crevice. So I can already see that my medial axis or skeleton in digital world will be highly susceptible to noise. And that's just something that is pretty much unavoidable. That, and if I threw salt and pepper into my image, then all of these medial axis lines will try to go around and in between these speckles, right? So if I had issues in my segmentation and I had very noisy image to begin with, then that would result in sort of expected issues in my medial axis. So take-home lesson on almost all of these morphological operations on segmented images is that quality segmentation or removal of the noise, something that is not physical, is very important. This is also just a fun, so this is application in object recognition in regular analysis of photographs. So if this is just a photograph of a phone, then basically this is what I get by image segmentation of this. And this is not an X-ray image, so this is the illumination matters. So I'm gonna get these speckles and issues, and then the resulting medial axis or skeletonization of this is something like this. I'm going to leave it to your imagination whether this is good digital representation of of a handle of a phone, which I realize that some of you, how many of you have at some point in your life had a phone that looks like this? Are you too young for that?
I did have one of those with the disc that you had to rotate.
Rotary phone? Yeah, that one, rotary phone. It's called rotary phone. So I can, fun fact, while I was in high school, I still had to use the rotary phones. And basically 2 numbers of my best friends in high school to this day, I know. It took a whole lot of pain to some of my best friends right now. I don't know. My phone knows their numbers, but I don't necessarily know them by memory. Oh well. Anyway, so I have a physical memory of the rotary phone and use to call them. So to this day, I can reproduce what those numbers are. So I can call their parents now. Anyway, so basically, you, just like in anything else, you have to figure out whether the digital representation of the object is actually to your liking, or whether you understand what is the level of noise in the image and how useful any kind of absolute numbers that come out of this are. So that's something to always have in mind with images. Okay, so just the very basic of how these algorithms work. They start with these candidates. So candidates are easy to label. And then after identifying candidates, I want to thin those objects down, because these candidates typically are, especially in 3 dimensions, thick and have too many extra voxels that are not necessarily simplifying my analysis the way I would want it. So in particular, I need to do what's called thinning. And this thinning, this is where actually underlining Euler characteristic calculation is important, because what really these algorithms do, they quantify topology using Euler characteristic, and they're just making sure that if I thin down an object and throw away some of the surface voxels or pixels, I do it in such a way that I'm not changing Euler characteristic, neither number of cavities, nor the holes, nor connected components. So basically, and that has some, sometimes there's some ambiguity in dependence on the starting point. So here's an example. Let's say that I have 5 pixels, and this is my original object, is all of these 5 pixels that are here. If I actually started thinning from number 1, so I would say, okay, number 1, if I start, depending on how I start thinning, okay, I might actually say, okay, I will throw, so if I look at this and I start from 1, I can throw away number 1 without changing topology of the object. So my object 1, 2, 3, 4, 5 and 2, 3, 4, 5 is kind of topologically the same, other than just its volume, but volume I can change. Topologically the same if I throw away this object, pixel number 1. So I can throw it away. I throw it away. I keep going. And basically, depending on what I process next, I can decide to throw away 3 and 5 and be just fine by leaving 2 and 4 connected. And of course, I'm assuming connectivity using corners, so I'm assuming 8 connectivity. Okay? So basically, my resulting thin object is this blue one. At the same time, I can imagine the scenario where I started from 3 and I was able to essentially throw away all of the others in the process and still remain, this is basically my thin version of this. Well, both of these, this 1 pixel is a thin version of these 5, and these 2 pixels are a thin version of these 5. My result is slightly different. They're actually physically completely different objects because 3 is outside of 2 and 4, but they're topologically actually the same. And plus minus 1 pixel, they're in the center of this, whatever you want to interpret as a center of something that is this small. Okay? So one thing that you have to get comfortable with is that the choice of connectivity you choose matters. Okay? And also order in which pixels are processed will throw away 1 pixel versus the other, and technically it's a topologically equivalent thing to throw away either of them. So which one you throw away depends on order in which you process pixels or voxels. So again, but the result is these 2 are topologically equivalent. Just don't get upset that they're actually completely distinct. This object is on the outside of this one. Okay. but they're both sort of in the middle, digital middle, though digital middle is hard to find in objects that are digitized like this. Okay, so again, typical outcome is this. And here, I know now why these pixels show up as my candidates before thinning. Now, often when I look at this object, I'm thinking about that center or a main central line as this. So essentially, to achieve this, I have to do some post-processing of the medial axis, and basically I can throw away these in terms of graph. If I understand this as a graph, this is sort of a branch leaf, sort of like I don't go anywhere important from this leaf vertex, so I can throw away this branch leaf paths, but that's basically post-processing. This gives me sort of what I often refer to as a skeleton, is post-processed medial axis to just give you the simplest object that you need in your application. Okay? So let's see, we have about 5 minutes, and I don't think I shared I shared the exercise, so we're gonna skip exercise and we're gonna try it next time. So basically we can actually do the test for this. And there is a skeletonized both 2D and 3D versions in Fiji. And then of course, we will do a little exercise with adding noise to it. So if you add salt and pepper noise, it's got kind of called good luck, you get a complex object. Now, in literature, just historically, it was started as description of shapes in biology, and by Blum in 1967. And it took quite a moment. This was actually, I think, if I remember correctly, images of leaves and analyzing their structure. In terms of review papers, there is a relatively recent paper, Curve Skeleton Properties, Applications, and Algorithms, from 2007. And this is for general computer science applications, if you will. Now, in porous media, it took a moment to get to images of porous materials. It took X-ray development in the 90s. So then naturally the algorithms to analyze those started in the 90s as well. So there's a lag of technology transfer lag of about 30 years. So one of the first algorithms that was implemented for the porous media applications is a so-called Lee, Kashyap, and Chu algorithm. This is a computer science algorithm, but it's again, it also included some of these cleanup operations that were important for porous media specifically. And then this Ma and Sonka algorithm. So just to kind of porous media applications, so here's one digital example of a very simple digital example. So these are my grains. These are grains, and the pore space is in white. And these colorful voxels are basically my medial axis, or colorful pixels rather than 2D, are my medial axis. What's again nice about this is I can see from here to here. I can come via connected path, and I can see whether I have a connection from one side to the other. So I can actually look at the connectivity in porous media. And I can also look at the tortuosity of this path. So I can see this path across, and it's a slightly larger than just a straight line, right? So that gives me this tortuosity of the pore space in porous media. Same thing here. If I go from here to get to the other side, I either need to go this way or this way. So I have, well, or all the way this way, but so I get more tortuous and tortuous. So I have multiple options to go from one side to the other. So I will overall look at the distribution of these paths from one side to the other and distribution of tortuosities. And that can also be, tortuosity is just a relative length from one side to the other by following this a network of paths versus just going in a straight line. And that can actually be used as characterization of porous materials. Okay? Now, these colors in this image also indicate labels from the GraphPhi algorithms in some part of the literature that that I grew up on, really. They're called burn numbers. Grew up in terms of porous media, grew up. So basically, you will see the red ones are those that are at least very close to solid grains. So here I'm pretty close to my nearest solid grain. Those are the red colors. Yellow is I'm a little further away. Blue and purple, I'm the furthest away from my grain, from the grain. So these are sort of like my centers of pores, so to speak, these burn numbers. They're essentially distances to the closest grain. So medial axis, ultimately, once I thin this object, it's organized as a bunch of digitized curves, and it can be organized into a graph. And once it's organized in a graph, I'm suddenly in graph theory and can apply all kinds of algorithms from graph theory that might exist that I don't even know about them. So this is where, when you abstract your pore space into a graph, suddenly you can borrow from algorithms that are literally used to analyze aircrafts and connections between airports. So that's something that is really useful and becomes powerful. So again, we have this now digitized versions of noise. If the nodes, if this is a graph, then great. This point here is a node of 4 paths. Okay, but so is this object. It's not necessarily just one voxel, so one, I have to be careful that what my node has a digital version, and it could be multiple pixels or voxels that are in one graph node, and that are connecting these paths. So that's something just to, there's a digital version of the graph and the graph as I would draw a graph analytically. So terms that are used in this area, and after introducing them, I'm going to stop, is medial axis. It's also sometimes referred to as a skeleton or a percolating backbone, and sometimes even deformation retract. This is from differential geometry. And then medial axis computation. It's also called morphological skeletonization or morphological thinning. So these are terms that are used both for the outcome and the algorithms themselves. All right, I'm going to stop here and we're going to start with examples next time around. Any questions? Did I put you to sleep on a Monday afternoon? Successfully? You need an extra shot of coffee now after this class?
Is it possible that you can upload this presentation?
Yes. So I didn't do this one. I did do the other one. So now I need to, I typically introduce first, then I upload.
Okay.
And sometimes I lag in upload. So I'm going to upload both. So I owe you this presentation and the video from last time and this time.
Okay, thank you.
All right. Any other questions? Okay. All righty then. I see you on Wednesday, and on Wednesday is where we have that write-up due, right?
Yes, ma'am.
All right. Okay. See you on Wednesday. Let me know in between via email if you have any questions.
Thank you.
Stop share, stop record.